Okay, the fourth question we have about these infinite cylinders is figuring out what the surface charge density is for the outer shell. It's a conductor, and we want to figure out, we know that some charge is going to move here. For instance, since we have -5 on the inside, we can imagine that will result with some positive charges here to cancel out that -5, and so we probably have some negative charge density on the outer surface. So let's go about calculating exactly what that value is. What we know is that if we draw a Gaussian surface that just goes through the conductor, our electric field is 0 there, so we know that the integral of E dot dA, which is always Q enclosed over epsilon naught, is 0, so we get that Q enclosed must be 0. So how much charge is enclosed here? Well, we would have, of course, lambda inner plus lambda shell, and we have to do another thing, shell, let me say inner, okay, because that's the charge that's on this inner part here, has to be equal to 0, and so we can solve this and find that lambda on the shell, the inner part, is just equal to minus the lambda on the inner cylinder. So that's part, they didn't actually ask about that, so this is just going to be equal to a plus 5 nanocoulombs per centimeter. But they actually asked for lambda shell outer. So how will we find that? Well, we know that the total charge on the shell is going to be equal to a plus 2. So I can write lambda shell, sorry about these subscripts here, inner, plus, oh man, lambda shell outer has to be equal to 2. And so we already know lambda shell inner is a plus 5, so we get a plus 5 nanocoulombs per meter, actually per centimeter, plus lambda SO, shell outer, is equal to 2. So lambda, the shell, outer shell, is going to have to equal to minus 3 nanocoulombs per centimeter. Looks pretty sloppy, but we got there.